In methodology, a system with unlimited resources is reviewed first, and back orders are allowed. The parameters involved are customer demand lambda, inventory position capital I, reorder point R, order quantity capital Q, ordering cost capital K, holding cost H, penalty cost P, and lead time capital L. Then a system with limited resources is analyzed, and back orders are still allowed in this case. There are some additional parameters involved. They are the amount of available resource W, the amount of resource occupied by one unit of good S, and the shortage cost per extra resource A for the algorithm. For both systems, we form the respective equation for the expected total cost per time unit, and we find the respective RQ that minimizes the total cost by using the suitable algorithm. From the case study, we know that first, the single item system consists of a manufacturer, a warehouse, and customers. Second, goods are discrete. Third, the demands arrive at the warehouse according to the discrete Poisson distribution with mean lambda per time unit. Fourth, the demands that cannot be satisfied immediately are back-ordered. The manufacturer replenishes goods to the warehouse with a constant lead time, capital L, after receiving an order. Fifth, the resource constraint in the system is considered to be the storage capacity. Sixth, the shortage cost is incurred when the storage space is insufficient to place the goods and extra storage space needs to be rented. From the case study, we know that there are some concept of inventory position is used. The first one, the inventory level is defined as the amount of goods on hand minus the number of back orders. Second, some goods have been ordered but have not been received by the warehouse. Such an order in replenishment is called an outstanding order. Third, if a good in outstanding order is assigned to a customer, it does not occupy any resource. Fourth, the inventory position, denoted by capital I, is defined as the inventory level plus the amount of goods in all outstanding orders. The above mechanism means that the resource is occupied only by the goods on hand and the unassigned goods in outstanding orders. Thus, the amount of resource occupied depends on the inventory position only. Under steady state, the inventory position capital I is assumed to be uniformly distributed over R plus 1, R plus 2 until R plus Q.
So from the part of methodology, we know that we need to deal with the system with unlimited resource first. After that, we do some modifications so that we can deal with the system with limited resource. In our model, we have our demand follow a Poisson distribution, and we also apply a concept which called inventory position, so that the sum of expected holding and penalty cost can be expressed as this function, and we can see that this function is actually convex respect to y, and negative of this function is a unimodal function, so that it will has exactly one local minimum point. After that, we can express our equation for the expected total cost by just adding up the expected value of this gy with the ordering cost. So we will have our equation for the expected total cost like this. What we need to do next is just apply the algorithm to find the optimal RQ so that we can minimize our CRQ. So this is the algorithm that introduced by the author. The main idea is like we keep repeating the iteration so that the RQ will converge to the optimal solution. As I mentioned before, we just do some modification with the system with unlimited resource. And when we deal with the system with limited resource, we have three more parameters which are S, W, and A. As we know, inventory position can be either non-negative or non-positive. So by combining these two cases, the amount of resource occupied can be given by Si prime, where I prime is maximum of 0 or I. And we know that the resource shortage will occur when Si prime larger than W. So we will have our expected amount of resource shortage given by ESI prime minus W prime. Since we need to combine with the parameter A also, we will have our expected shortage cost equal to EASI prime minus AW prime. Without loss of generality, we can just rewrite AS by S and AW by W. So we will have our final term like this. So after we do the modification, which is just add up one more new term beside the equation, we will have our new expected system cost like this. So this will be our new expected system cost equation. What we need to do next is also by using the algorithm to find the optimal RQ, because we can see the function gy is also a convex function and negative of this function is also a unimodal function. So we can just apply the algorithm that I introduced before to find the optimal RQ to minimize our CRQ. So to understand more about this algorithm, we will further explain by using some suitable numerical example and also explain by using coding and Excel afterward.
So here is the numerical example. Consider the parameters with following values. The demand mean lambda is given by 13. Holding cost K is 1042. Lead time L is 1. Holding cost H is 13. And penalty cost due to backorder P is given by 247. First, the solution R tilde Q tilde with unlimited resource is obtained. Next, for the system with limited resource, assume that the storage capacity is 30 and each goods occupies one storage space. The rental cost for each storage space is 100. Then we have additional parameters W equal to 3000 and S equal to 100. The solution R star Q star with limited resource is obtained. By the algorithm, we can obtain the following optimal solution. We obtain these values by using MATLAB coding. So this is our coding. We have to key in the values of our parameter here. For the case with unlimited resource, we can let W equals to infinity. Now we run the coding. And we can see that our function g is convex and has one minimal point. We also obtain r equals to 11 and q equals to 48. The optimal cost is approximately equal to 608. Now we let w equals to 3000 and we run the coding again. We obtain a new gy and our new r is 10 and q is 25. The optimal cost is approximately 823. This is how our coding works. We know that the function g has only one minimum point, so we can list down the value of gy from y equals to 0 and find the value of y that minimizes gy. For this case, y is 19. Then we proceed to find q min and q max. The first iteration, both of them are taken to be 19. Next, let r be q min minus 1 and q be q max minus q min plus 1. Then we calculate gr plus q plus 1 and cr plus q. Then we check the condition whether the minimum of gr and gr plus q plus 1 is greater or equal to crq. If false, then we need to do the next iteration. Also, if gr is less than or equal to gr plus q plus 1, we minus r min by 1. Otherwise, we add q max by 1. Since this is false, we add q max by 1. Then we do the same for each iteration, and finally after 48 iterations, we obtain our optimal solution. The algorithm for limited resource is exactly the same. This time we obtain our optimal solution after 25 iterations. So basically this is how our model works. Thank you.